So we do have a lot of visitors here, I know, from Karlsruhe, but also from elsewhere in Ontario. So I'll just do a territorial acknowledgement. We are located on the Haldeman Tract. So this is the traditional territory of the Anishinaabeg, the Neutral, and the Haudenosaunee people, for those of you who don't know. So our main campus is on the land granted to the Six Nations, so that includes 6 miles on each side of the Grand River. And our active work is towards reconciliation, and that's taking place across our campuses through research, learning, teaching, and community building. And we do have the Indigenous Initiatives office that is trying to direct that effort as well. So today we have Dr. Mário Franca. He's a professor of hydraulic engineering and water resources management at the Karlsruhe Institute of Technology. Before KIT, he was at Delft, TU Delft, IHE Delft, UNESCO, and held senior academic positions at Lausanne, New University of Lisbon, and Coimbra. I don't know how to pronounce that one. Sorry. But anyways, let's welcome Mário Franca. Thank you.
Okay. Okay, thank you. Thank you for the presentation. Do you hear me well? I think. Yes. Okay, so, well, Bruce presented me already. So I'm professor of hydraulic engineering and water resources management at the Karlsruhe Institute of Technology in Germany. I'm here with some colleagues in the framework of some search for collaborations with the Waterloo University. And, well, I want to thank also Bruce for the invitation to do this talk here today. I'm going to make some notes about the floods that happened almost 3 years ago already in Germany. So we did some post-incident studies, and these are reflections a bit what could have been done, or how could we have thought this a bit better, and I think they're important to do for the future as well. And in the end, I'll present also some new results that were inspired by this unfortunate incident. Just before, I just want to present ourselves a bit. So in Karlsruhe, we have a group, well, an institute, which is called the Institute for Water and Environment. We have 5 professorships. Olivier Hayf is here as well. He came to visit as well. David Evans is in my group. He's here as well. He came. And we embrace research since the very fundamental aspects of fluid mechanics. And then there is a kind of a grow-up until more practice-orientated research. So we do the bridge between the fine-scale research, if you want, towards the application. We have two positions that will open very soon, just in case we need good candidates. So they are tenure track positions. One will come, hopefully, before the summer, but administration sometimes takes time, which is in fluid structure interaction. Another one in urban water management will come a bit later. Okay, we have to search for good candidates because they are rare these days. Some more information about ourselves. This is also since we are in the search for collaborations and internationalization of our programs. We have a master in English on water science and engineering. It's an international master with 3 profiles, one more oriented to water quality, one where me and Olivier are, which is more fluid mechanics and hydraulic engineering, and one more on hydrological processes at the catchment scale. It's a 2-year program, all taught in English, and maybe an attractive opportunity for some of the students as well. Of course, these are the best pictures from the visits. Of course, we show what we have the best. So this is my group specifically. I will just go briefly to them, but as you can see, our aim is more on the practical side, on application side. As I said, we have a laboratory with 25,000 square meters, so it's a big laboratory where we have installations more the size, bigger installations for also reduced models, consultancy with reduced models, but also for fundamental research. Some examples of research we do at the moment, and they are all more or less related with as I said, hydrodynamics aspects, but also mechanics of transport of sediments, of plastic as well, and also some eco-hydrology programs as well. So, okay. Maybe what's more interesting for the talk of today, we hired someone last year, Ali Purzangbar, is a postdoc, and is trying to apply new techniques also to speed up the process of understanding floods and also to speed up the process related to emergency planning in terms of flood management. That's all, okay? Let's go for my talk now. So first, why I'm talking about floods? Am I talking about floods? Probably Bruce or Colin or something have heard me talking about floods. I've talked about sediment transport and turbulence and these things. But I worked as a consultant several years, and I did many flood management projects. And this is my town. And I was a teenager in this year, and I was just behind this, stuck in the flood with some friends. It was 23 of December, birthday of my best friend, and we went to her house, and we got stuck by the flood. So it was quite exciting. When you are a teenager, you are insensitive. So I have some sensitive to floods, and I will pick up on these photos a bit later to show something curious. The talk of today will go through these aspects. So I will just introduce a bit the July floods with some information that I have, very general. I will just make a challenge with you here, and then I will do reflections, which are basically, as someone working on rivers for several years, we look at floods, we look at what happened, and these are things that I think we should be looking at also when we plan floods, okay? And I will present somehow this is inspired for what we observed in the floods, and I present some new results of research that we just published last year and this year. This is where the floods happened. So this region, the main affected region in Germany was this, here near the border with Belgium, Luxembourg, and somehow the Netherlands as well. And the main problems occur in the Aar River and in the Erft River in this one, and this, which is this one, in this area here. So near the border, the three countries, or the four countries are affected, but Germany was heavily affected as well. These are general numbers, but just to have an idea, so 6 inches of, I think I did, I hope I correct, I did well the conversion, so 150 millimeters occurred in, well, less than a day. It's a lot of water pouring down, and this was due to, well, a convective storm that just stayed there for some hours and just poured down all the water that it has. Big numbers, okay. I think this is not even updated, I'm sorry, so I think it's a bit higher, so almost 200 fatalities. For a country like Germany in the center of Europe, for Europeans, it's a catastrophe. It's even damaging our way of thinking as well. So it was quite a change, a paradigm change, and it's somehow prompted lots of research about this as well. Just some examples of big numbers. 62 bridges were just collapsed in one valley, and many other disruptions. For several days, there was disruptions in the in the communications and in transportation services. So, it was a significant disaster that occurred. Now, I put a question, so I can make I would like to make a kind of a game with you. I think that's possible here. And I don't know if you were Boy Scouts. I know that probably you were, and you probably did this game. I don't know. Do you know do you know the Kim game? Okay, so it's just, I will show you some images, and you just have to put in your mind what you saw, and then I take the images, you just have to see me, to tell me what you saw. Okay, is that okay? Can do this? Okay, we do it fast, okay? And the images will be I will count until 5, and I will change them to make it fast, okay? So the first image, just see what you have in your, what you can recall. We can go to the second image. These are all from the floods, okay? From those floods in 2021. I think I have 4 or 5. Okay. So what did you see? Can someone tell me something?
Wood transport.
I'm sorry?
Wood.
Wood?
Generally debris.
Debris, general debris. What else do you see? Many things, right?
Ambulance.
Ambulance, okay. Or cars, let's say, vans.
Flood water.
I'm sorry?
Flood water.
Okay. It's the first time in 2 years that someone says water. So you screwed the game, okay? So the idea is that everybody will say everything except water. And That was the question. Okay, we have to talk later about this. But the question is that where I wanted to go, and I did lots of flood planning as well. And usually the flood maps where we use in the municipalities are these things with the topography, and then we have a blue thing, a blue dot, and we just, that's what it looks. But we see the floods. It's not that. It's completely different. So apparently we are not planning well. Okay, we are doing the best we can. But we have to consider something else than just the water. So that's where we come to the reflections that I brought here. And we will see lots of images like this, quite catastrophic as well. I'm going to talk about 4 topics. They are very personal as well, so they are personal reflections, so they are questionable, of course, and we can discuss them in the end. And the first, it's what I said, we should look at the history of the valley, and I'll show you what. And probably it depends a lot on the countries, but in some countries it's still possible to construct, for instance, in floodplains, in places where we saw things happen in the past. And I just brought this example. So this is, I think well, those studying rivers, they know what is this. And you know what's an oxbow lake. So a fluvial hydrologist or hydraulic engineering should know these processes that happen and should know when they see a landscape, some remain oxbow lake or something. And probably should know also that we should not build there, right? So this is one of the things we brought. And this oxbow in the Altenburgs, which is in our valley, in our river, one of those 2 rivers affected, this is what happened. So that's the effect. So the flow goes like this usually, and this here, it's this here. This. So basically the development, the urban development was all made in the Oxbow Lake, which of course with time, well, things could happen. So this is first reflection. Maybe it's a bit obvious, but okay, apparently it's not so common to think about these things yet. There is an advantage downstream. Well, this is a small one, but of course all these Oxbow lakes, all these lateral lateral areas of the flood, they will contribute to somehow mitigate the flood. So maybe it's even good that we are here and that we can activate them. But of course, settlements in these areas, well, should raise some flags and should indicate that we should not do it here. They are reconstructing in the same site, so just in case. I think that's one of the problems now. The second, I put this image as well. I'm not going to go on these details here, and Colin is here. He will even detect some errors that I can do about this. But we know some things that happens in the rivers. We don't know everything, right? But for instance, we know how the flow processes in a riverbed. These are images from classical studies that we found in the literature. And again, when we do our flood propagation, typically, okay, maybe in this channel we'll use a 1D model, we'll just propagate the flood laterally, but we could at least see, oh, there's a bend, there's something that can happen here. So it's a second reflection. We know better than we are doing, I think, in my opinion. At least we have more knowledge than we are doing. So this is another river. So this is the area as well in Schult, another town. I'm not sure if it's downstream or upstream of the other, which has the R going here around with a nice meander. It goes around here. And this is a pre-flood, a pre-incident images, if you want. So it could not be very hard for a student in fluvial morphology. Imagine that in a flood, we could have some deposition here and some deposition here and all along the valley. Again, this is what happened in the valley. So this area here, it's not indicated, I'm sorry, but it's somewhere here. And I think this is an image from the top here. This is more dramatic. We can even see the streamlines of the flow almost with the trunks. So again, the question, yes, maybe we should have known better. And of course, it's very hard to model the whole valley if we want to do some efficient thing in the company or something. But we could just, after our modeling, we go around and see if there is something that, okay, maybe here we may have a problem, maybe here we shouldn't have a problem. So second, reflection, the complex hydrodynamic processes, I think we already know enough to somehow integrate them, even if it's just ad hoc and a bit simplified, integrate them in flood management. The third reflection, it's about landscape singularities and fragilities. And well, we know that if there is a singularity in in the flow channels. There will be flow separation. There will be phenomena of local acceleration, deceleration, and we know that they will have also impact in the flow resistance, in erosion, local erosion and deposition, and etc. So there are some examples clear of not very well studied singularities. The most obvious singularities in the river, maybe it's the bridge piles. I'm sorry, I didn't. That we are not studying well, and then we have these, well, problems, specific and singular problems in the valleys when the flood happens. As I said before, in this valley, 62 of these bridges was destroyed. Of course, the financial impact of this is huge. I pick up another example, which I think is more interesting. So let's look at this image first. This image is the flood map for the extreme flood. So that was done to the municipality. So there is the river goes somewhere here. I'm sorry. Yes, this is the river here. And the flood map previewed, it's not very clear, but the darker blue, I think it's the inundation areas. The river goes like this. And it was previewed already that mostly this area of this town will be flooded. But this is interesting. I just checked this in the internet. These are public things in Germany. And you could see there is this special feature here. We'll go here and I'll explain what you have. But someone that did this flood map indicated here some strong velocities in this area. So this is a Google Map image of the same area. Before the flood, the river goes here. And what is this here? This is an old mining, no, it's still active, I think. It's a mining pit where they extract gravel. And this is maybe 20 meters or more deep, it was. And what the flood map says that somehow the water will go in the flood, the pit, right? But nobody really, okay, fine. So we look at this and we do our emergency planning and nobody look at this detail. And what happened was this. So let me say if I explain. So see this image, this line here, and this was reconstructed by me. So there is some uncertainty. But basically, the flow indeed went inside the pit and just carved this. So the pit is here somewhere, carved this huge crater of 20 meters, which just stopped in this building. So what we may argue is that maybe if we do our flood maps, we can even look at our velocities because we have that. If we want as well, if we have, I don't know, even an ECRAS simulation, we can have even the bed shear stress. It's an estimation, it's a model, but fine, but we can have it. And we just put on the top of a geological map, maybe we could have imagined at least that, whoa, this could happen. We could not model this, but some red flags can be identified at the planning phase. And I don't know well what will happen, but something will happen. So maybe we reinforce this area or we prepare for this area or something like that. There were other singularities and fragilities, well, I call it like this, in the landscape that could have been previewed maybe with a better inspection of the results of the flood mapping and the flood planning, flood emergency planning, sorry. And I have this final, let's see if we understand. So this was the original pit was here. This is where the water in this section here. This is that building that just stayed hanging there. And this is where the erosion happens. So the channel, the river will go like this and like that. And it just dried afterwards, I think, yes. And at a certain moment when this happened, there was an advantage. The flood stopped downstream because that pit was so big, and of course this is so big, just absorbed the rest of the flow. Okay. And there is also another thing that I even said, because there are lots of these mining pits spread around Germany, because especially in the valley of the Rhine, because it's pretty much alluvial and full of gravel, which was quite explored for construction. So maybe we could even use lots of these abandoned pits for laminate floods or something one day. Well, that could be done. Final reflection, it's about how the boundaries are changing during and before the flood. And this is, again, to think about how we can do, well, how do we do the flood planning or the flood management? We look at the channel, we go with the LiDAR, we take the topography today, and we do our modeling. Even if tomorrow the topography is different, it stays there for 20 years. I don't know how many times you have to review these things, but we don't really care. But the truth is that if there is a flood, things change. Of course, first they change in time before the flood, and they change during the flood. I bring this example, which is, it was not proved, not validated, but it's something that I did some years ago with a colleague from Lisbon, Rui Ferreira. I think some of you know. And we did some consultancy for dam break, emergency plan for dams. And this was a dam break study. But, well, we are kind of academics, so we decided we are going to look further. So we used the model, that is the model from Rui Ferreira, where we can see the dam break propagation, but we also can see morphology changes in the valley. And this is the valley downstream the dam that we did. It's a dam in the south of Portugal. And this is about 3.5 kilometers downstream of the dam. And this is the result. This is the bed, how the bed changes. So this is the delta Z, how the bed changes downstream the dam in the case of the dam break. And we detected this in our simulations. So there will be a huge erosion pit and then accumulation, which exactly corresponds to this narrowing of the valley and where there is old bridge. And so the access to the dam, we have to cross this bridge and go somewhere there, and the firemen and the civil protection is here. So we had to change we forced the civil protection to change all the paradigm of emergency, because we told them probably this dam will not stay in place if there is a dam break. Well, we did this. We were succeeding in convincing them. They took us serious, but the next studies, and we told them maybe you should ask people to do these studies with morphology changes, because there are things we don't see. Well, I don't think this was accepted, but okay, this is an example of how we should consider, this is a case of a dam break, but we should consider morphology changes. Of course, the models are, well, if it's 4 meters or 3, but something will happen there. Actually, if we look at it, it's obvious that something will happen there. So many things happen during our floods. So erosion, local erosion of bridge piles, destruction. This was curious. The water just entered a tunnel and just provoked a huge erosion here. This is, we don't see, but there was a huge erosion here in the position that changed completely the aspect of the valley. And I think we start having some models, even with some approximation, that tells us the main morphological changes that may happen during a flood, and we should use it. But I'm going to talk about other things as well. I think the valley has multiple changes at multiple time scales. So these are the time scales during the flood. But for instance, this valley in the city, in the town of Dernau, this is the R Valley, changed also along a century. So in the 1800s, they constructed the Ahrtal trail, rain system, or it's called Ahrtal Bahn, the railway of the valley of the Ahr, which just run, I think it was a beautiful scenery thing to do, which just run through the valley. So let's see the valley. The valley, you can see the river comes here, the river Hall. This is really a lateral floodplain, very flat. You cannot see here, but this area here, it's quite steep. So the banks are quite steeper here than here, but it's quite carved, and then it just widens again here. So the Ahrtal Valley was constructed here, and along this part here, they constructed 4 bridges, but those old bridges, this is 1800s, or late 1800s. So all these 4 bridges collapsed, so the Ahrtal Valley just disappeared. Well, we don't know quite what happened, but probably they collapsed, they got clogged, then there was a dam break. But by clogging, what happened in the valley, in the Dernau town, what happened was a flood that was much higher than before. And our hydrologists and meteorologists, they could reconstruct this huge flood before the construction of the train system. And they said, don't ask me the methods, but they said the maximum discharge was pretty much the same as we had 3 years ago. But the effects, it's 2.5 meters more. So again, there was a 100 scale change of the valley, but when we did our modeling, we just Probably we modeled this with a 1D model or something. We just put some coefficient of resistance, extra resistance because of the piles, but we didn't account that here we could have a completely blockage of this valley, at least for some hours, that will inundate all this part here. So the bridges are here. We can see that if you have a trunk or something, very easily they get clogged. We don't have ice jams like you have here, but it's the same thing. Okay, and I think again we could do a bit better than this. We don't know much. Well, we know how wood is transported, is recruited in the landscape. Mostly we have papers about it, not really textbooks about it, but we can already have an estimation of how much rubbish will come to a section like this. Okay, and now I always go fast. All this prompt many research in Germany, in my group as well. We start thinking about what can we do to change things, and we start studying transport of large-scale debris, urban debris, let's say. I think this is something you are doing here as well, so it's very nice that I can explain. And the first studies, we have just published them about this subject. So, again, my town in '89. So this was a huge flood. Okay, it was, I found it funny in those days, but of course it was not so funny for the population, for the rest of the population. And I decided to give to DALL-E, this artificial intelligence thing, generator of images, and I gave him these images, and I just made him a question, which is here. To adapt the pictures as if the flood was happening now, in December 23, okay? So it's the same flood. Of course, it's not perfect. I don't think we have trains on the top of trains in there, and I think, but the beards are there, the phones are there. I think there is some interesting things that they captured. It's interesting. What's most interesting is how crowded the streets are now, and they were not. So somehow the DALL-E could figure out these differences. And again, there is more going on than the flood. And of course, if you imagine a flood in a situation like this, or a flood in '89, where we used to play football in the streets, the cars, there was one every half an hour. There is a big difference, and this is what prompted us also to investigate how these things are transported. So, what does the European Floods Directive or Water Framework Directive, I think that's the name, says about considering other things than water in flood management? Just for information, in Europe, in the European Union, we have these large-scale laws imposed by the European Union that then slowly they have to be adopted by the countries. And there is one that it's regarding European. That is regarding flood risk management. And some things in the laws they are compulsory, and others are suggestions, like the consideration of the sediments and debris. It's suggested, but it's not compulsory. But we know that debris and sediments moving, they just, cause this, and we will have extra resistance, blockage of channel networks, and of course even destruction of or impact in buildings and infrastructures, injuring people and animals, etc., etc. An interesting thing as well, we tried first to classify things very simply, sediment and debris. This is the first attempt. We start, maybe natural and anthropic, organic and inorganic, small and large. And the interesting thing is that all this year, when you see pictures of floods, not even 100 years ago, 40 years ago, these are not so present. So all this, it's something which is much more recent. So it's things that, changed in the last 50, 40 years. We see this much more in the floods than before. So we decided to kind of have a roadmap. So how can we go and consider this until the scale or the engineering practice, let's say. And we defined all these steps. So first we want to see what's that. So how to classify what's in the floods. First they will have to move. How can we figure out how they move, how they start moving? It's just like sediments, okay? We do the same. Then we have to characterize the transport. How do they transport? How do we integrate, for instance, in a shallow water equation model, the transport of a car, of a bin? And then, well, I'm not going everything. So the idea is to incorporate this in flood modeling. It eventually go down to the planning of measures to increase cities' resilience. And this is something we have been talking. So how can we improve our cities that they are more flood friendly? They can evacuate better floods, and they can also be less dangerous for the people that inhabit them. So this is a long pathway. So we tackle two parts of this, and we have someone else to tackle this in the third step, let's say. And I'm going to present results of this. So this is what I call search. So just to classify, to identify, classify, and characterize what's there. And we also made studies for the stability of this. How do they start moving or not with the floods? So the first part, these are, so what we did, we just collected post-flood imagery. So we went online to the, well, we didn't go to newspaper, we don't need anymore. So we go online to the newspapers, to the social media, and we did our search. So we identify, we classify, and then we also quantify the frequency and prevalence, so how much of this occur nowadays. And then we also extract some basic properties of mass and geometry of these elements. I'm going to just talk a bit about this part here, or show some results. So basically what we did was just go online, we take a picture, and we see, in this picture, do we see cars, do we see caravans, we see, so that means the prevalence, and then we see how much we can see in this. And we obtain, well, there is a certain logic in the search that we defined, and I think we obtain quite stable statistics as well. So we put students identifying all these things. And we could first make a classification. So based on what we observed, we classify them in, well, there are two big groups. So the big things, let's call it like that. So it's the things that are more or less compatible with the dimension of culverts, of normal culverts. And then let's call the small things, which are also very prevalent in floods, but these are maybe more clogging drainage, urban drainage. And of course, if they are a lot, they will also clog. So by classifying them like this, we start to having a kind of an idea of how to cluster these objects according to certain properties, to certain characteristics as well. So we classify them. This is our classification. It's questionable, of course, but I think it's a first step. And the second was to study frequency and prevalence. Basically, it was to see how much they were present in the images. So how many images had cars, how many images had the things. And then the frequency, it's how many are in each image, how many they are. So an interesting things, for instance, one of the most studied, there are some studies on these things already, but it's mainly for car stability. And they are only, but a lot, of 31% of the observed material in the floods. And for instance, if we look at the large objects, this big classification, 41% of the things that we saw are these large ones with high potential for clogging the channel network. And then, of course, we did some other considerations. And this is the kind of, well, what we have so far as the state of the art that can be observed in the floods that we analyzed. And then what we did, the next step was to pick up on all these characteristics, pick up on all these types of debris, large-scale debris, and make an analysis to understand, will they move or not? Under which conditions do they move or not? So first, we had to think a bit what are the main parameters that if we make a mechanistic analysis are relevant for the stability. And this is just mechanics, right? It's just, I'll show the modes of instability, but it's just, well, dimensions, weight. Also, what we may call a kind of porosity function. For instance, a car has a completely different exposure to the flow if the flow it's under the, how do you call this, the clearance or above the clearance. So we took into account all this for all those those elements that we identify as the main ones present in floods. How did we do this? We went to catalogs, okay? My son was 1 week to seeing this in catalogs, and we had lots of students like that. We paid them, of course, to identify, to see. But of course, cars have, okay, trucks, cars, they have different dimensions. First, let's just look at the limits of stability. So this is just classical mechanics, right? So what can happen to these objects? They can just float, right? They can be dragged, or they can topple. And this is an example of what we study for a trash bin. So, well, this is how we divide it. I think this is just simple mechanics. And we did this to all those objects, to all those variety of objects. And as I was telling you, of course, the cars change a lot, the bins change a lot. So what we did, we just took extremes, and we just ran Monte Carlo simulations to combine all the possible elements to each one. So we had a kind of a stochastic view of what we may have. And we could produce this kind of stability curves. So this is for each one of the elements, and this is for, well, they are all here in this place. So how does this work? So we go to one of these, I don't know, for vans, for instance, which is very popular in Germany, and people like to go on vans on vacations. Well, I didn't choose the good one. That's maybe two-wheelers, which is motorcycles and motorbikes. They are here. So they have this curve and have some uncertainty. And what this curve says, depending on the velocity and on the height of the flow, it will be stable or unstable. If this combination of these two, it's under the line, it's stable. If it's above the line, it's unstable. It's a kind of a shield diagram, more or less, okay? A stability diagram. For all these elements, and we even had some kind of an abacus thing that we can even, for certain slopes, and considering uniform flow assumptions, of course, we can just go here and have an idea of how much, for instance, a large heavy vehicle will change. So if we have a slope of around 1%, this is the smoother, this is the rougher. This is explained in the paper. I'm going a bit fast, of course, but this is more or less the range that you can have of combinations of velocity and water height for the instability of a large heavy vehicle. Okay. Of course, it's a lot of information. We don't need to go in detail, but the question is that there is always something that we can introduce in the flood map. And these are curves that are very well defined, if you want, and we can have already at least know in this street, at this moment, if there is this flood, how many of these will move. Okay. Next step will be, where will they go? And we also did a nice, a simple exercise with some simple considerations, a normalized flow, just to understand in the flood what is, if this is a discharge, what is first mobilized and lastly mobilized. So we don't need to go in details, but it's also interesting to know if there is a flood, what comes first and what comes afterwards. This is more like an example what can be done with a real case, okay? How we can handle this data to a real case. Okay, these are the main conclusions of this. We are here, so I think, and of course everything is questionable, everything probably can be more completed, done with more criteria, but at least we have an idea of what's there and how the things can be moved in the urban landscape, and elements that amplify clearly the flood hazard. And of course, we need to couple this with aerodynamic modeling, so that's the next step. And of course, this may be useful for future adjustments of the urban landscape. Next steps, it's this this phase here, the transport of large dB. We have someone already, and we are in kind of a parallel study, studying this very small liter. It's a collaboration with the University of Coruña in Spain. We are trying to understand how garbage in the street will condition the drainage system in the cities. Okay, this is kind of a parallel, but it's somehow related project as well. And okay, this is all what I wanted to say. This is just a final image, wrapping up more or less what I wanted to transmit. So it's not only about water, it's mainly about many other things. And we saw problems related with changing morphology, well, I think many of us study sediment transport and morphology changes. We should incorporate somehow the knowledge we have about this and about more complex flows in flood management as well. And this is what we are doing now, trying to incorporate also these elements. First, to know how they move, then we have to know how they are transported, where they can clog, and somehow understand how we can incorporate this in flood management. It's also not clear in our minds, because of course the street in Christmas Eve has a completely different occupation than the street in another day. So this stochasticity, it's quite interesting, but should still be thought, how can we incorporate this in flood management? And thank you very much for the attention. Okay, and I open to questions as well.
Yeah, thanks, Mario. We do have time for some questions, and I'm going to ask you to use the microphone so that things are properly in the sound system.
So thanks, Mario.
You came all along.
But I can't help to resist for a small comment, maybe for your disclaimer comment actually about the politics. For information, and the German government is putting in for this flood, the air flood, 30 billion euros plus insurances money, with one restriction: to rebuild the existing. In other words, when the house was stripped off, rebuild where it was.
Yeah, that's a condition for the insurance, to rebuild where they was.
Yes, a simple thing.
Yeah, I know we have similar houses being rebuilt in places like Cougar Creek in Alberta and other places.
So at least it's not only for
it's not unique.
in Germany.
First off, thanks very much. Some spectacular images, so thank you. So one just kind of simple question and then a more kind of probing question. So the first one, in your entrainment model, did you consider the orientation of the vehicles?
No, we're just considering the worst case that let me think, because it was Daniel Valero that did the details, but we consider the most exposed surface. Yeah. Okay, so it's perpendicular to the most exposed surface. Yeah, that's how we consider it, yes.
Because when we see the flood going down streets, cars that are parked, I mean, maybe there's angle parking in the US, but usually they're parked beside the street, along the curb. And so they're probably exposed, not in that axis.
Yeah.
Anyway.
No, but this is where that roadmap, I think, should lead to that. In some streets, you should say, don't park like this, park like this.
Oh, yeah.
Or just you put just a berm that maybe, so, but there's still work to do. But the idea is that what I call redesign the urban space to be more resilient. Okay, that's the idea as well. And the same with the bins and all the other rubbish that we find. Yeah.
Okay, and then one just a curiosity question.
Yeah.
The sediment entrainment from the mine pit.
Yeah.
Do you have an idea whether the concentrations of the sediment and the resulting flow went non-Newtonian? Like, do you have an idea how concentrated it would be?
No, I have no idea. And I didn't think about it, to be honest. I would say, no, I would say that it didn't go Newtonian. But maybe locally, I don't know.
Yeah.
But I think it was like a dam bridge, mainly. And the soil was very poor, let's say. So it was very erodible and very deep. And this is something that with the geological map, you could have seen, you know. Mm-hmm. But no, these details of the flow, I didn't go there. No. We don't even know the velocities, I think, because, well, what is published is just, there are some arrows there. I don't know, someone put that in the maps, but we don't know which velocity they mean, so, okay.
There's, just to follow on that, so there are some historical floods in the Ottawa Valley, which has Leda clays, which are very easily erodible clays. And there's has been retrogressive progression of scarp slopes, gorges, basically. Mm-hmm. And I have never asked myself the same question I just asked. Okay. So it's, anyway, thank you.
Okay, no problem.
Any other questions? I know, oh, sorry. Sorry, there's one here first.
Thank you so much. I just have one question that I'm not quite clear is about the...
Let me say, I don't hear well.
Oh, I just have one question that I'm not quite clear. Is thank you for the. Yeah. It's about the one using calculation to rate the depth to give the initial motion for the vehicle.
Mm-hmm.
Could you go back to the figure?
Yes.
Yeah, the next one. Yes, so why a higher depth in the figure F? Minimum depth H will generate less velocity.
No, this is not. This is a graph. This is different. This is if you have this depth and this velocity.
Yes.
You have a point here, so that means that basically everything will be movable. So this is like a stability diagram. So you have a line, everything above. So these will represent the flow conditions. We mean that it's unstable. Everything below means that it will be stable. So it's more like a classical abacus to. And this curve gives you the limit between unstable and stable.
Oh, yeah.
So, but it's not a computation of flow.
Yeah, I thought the velocity is
No.
give the initial motion of the vehicle. So
this will just tell you it moves or not. Not even the type of movement. If it's buoyant, this we didn't. So we just put everything here. Yes.
Okay.
So it will be movable.
Thank you so much.
No problem.
Thanks, Mario.
Yeah, thanks.
That was a great talk. Actually, same comment as Colin had of the head cut coming out of the gravel pit was extremely impressive. Haven't seen.
It was all the news, all the news. I don't know.
It was, yeah. Those are the ones that I think that need to be conveyed a lot more around the world with respect to the impacts of changing slope or gradient very quickly on conditions. This was more of a curiosity of from the analysis and the initiation of movement of various particles, shall we say, the size of a caravan, if you were. Is there any plans or thinking about doing it more as a turbidity flow? Because individual particles are one thing, but when you actually aggregate those together with multiple particles and or different densities of mud and debris and things, that takes on a very different animal and actually its behavior.
I would not call it turbidity, but yes, maybe pack behavior or something.
Yeah.
What we are starting to we didn't start, but I hope it starts soon. It's to understand one element, and then, what we want to do actually we did this mechanic model for instability, but it's too complicated now to resolve the problem. So we are going to make observations and make surrogate models. So this car, it's a point in the flow that has a certain law of forces that will influence the flow in a certain way. So, or not. Maybe it's just something that you can just put it like gradient and it will be transported and doesn't even influence the flow. So this is where we go. So one by one. And afterwards as well. But it will be always a statistical model to be inserted in a shallow water equation model or something. That's how we are going to do it, because it's much faster as well to implement and simple. So yes, first step one by one, and then, but I don't know how yet. But
I think you can numerically nest it. It actually makes more simplifying.
Yes. Well, we hired Davide to do this kind of thing, so probably, but I don't know how. But yes, that's the natural evolution. We are also interested in transport of, which is some of wood logs as well, and of course they can be individual, kind of packed and congested. So, but yeah, we are still. But if someone has better, if someone can shortcut the knowledge, the best, of course.
Hello, so thanks for the very interesting talk. So you showed an image of destroyed building and you said you should have known better. I think the fact that a location is flooded is not a reason not to build there. It's all about probability. And if you want to convince them, you have to show them that on average, the flood loss is going to be more expensive than rebuilding.
Yes,
right?
Yes, it's all about probability. Well, that yes. The answer yes. But I think the idea is honestly is to first pick up, grab the maps we have and just identify red flags. Maybe it's not even a problem, but okay. But if you just, I think we have much more information than the one we use. We just put information together and we identify, like the pit. Oh, maybe it happens, and then we just go. You go, and then you do a detailed study, and you can either live with it, probabilistically, or we can just intervene in the landscape and improve something. So I think that's more or less the message here. But of course, everything. Even this transport that we want to do, these functions that we want to do, the transport of cars or bins, everything, it will be stochastic. It will be a PDF or something. And it comes here with the flow. And there's a probability function where it may go. So it will be very, very...
Yes, I agree. It's going to be stochastic within one simulation of one event.
No, but that's how we think you should have many simulations of, for instance, a street full of cars. First, we should just the distribution of cars in the street. It depends on the hour of the day, on the time of the day, on the day of the week. Okay, just so it's a function of distribution. Okay, I may have 20 or 100 cars or something in the middle, and then I may have a flood combined with this, and then they may transport it or not. So that's the idea, but of course it takes time, and but that's where we like to go, you know. And in this street, probably gets clogged with this flood.
Okay.
And then we can make an action to reduce the probability or not. Okay.
Okay, finally, last comment. If you remove the politics, then that's the best way of not having anything done.
If we remove
the politics and human behavior from the problem.
No, yeah, that's what I said. But in all the proposals I've been involved now with floods, we even have psychologists involved because that was one of the main things that failed in Germany apparently as well.
Yeah.
Okay.
So perception are more important than fact in doing this kind of stuff.
I think both, yes, but both. But and one of the problems apparently in the floods of Germany that someone told me, a psychologist, is that people just they are not aware of the natural dangers anymore. So they're expecting for the message of danger, which didn't come. That was one of the problems. But they don't look at the river or something. They're just there, and then they were just washed. So this happened apparently in this flood. So, thank you. But this is a personal communication, not validated.
I have kind of a general question, I guess. Like, I know the 2005 flood in Switzerland was very important for changing people's ideas a little bit about what the river should look like, and maybe that it was actually dangerous to have these very narrow floodplains. Mm-hmm. Is there a similar feeling now in Germany that they should be having wider floodplains with more setbacks and more room for dynamics, or is it, as you said, mostly about rebuilding what was there before?
Well, to be honest, I've no idea if the politics is changing, but for instance, what I know is that the insurance and the support from the government to reconstruct is if in the same place, which is a bit bizarre, but I think some groups are working on this a lot on debris as well, like in Aachen and also in Dresden. But I don't know, is there any change in the politics? I don't think so. It's more the scientific awareness that's clearly above what was before. Everybody's concerned, but I don't see this being drained to the politics.
Essentially no societal pressure to change.
There is not. No. Well, you have to... Yeah. It's also... And you know, Germany is a federal state as well, and flooding is responsibility of the states, and to put them all together as well in the common framework and this thing, it's not easy as well. So it's and then there is for instance, there is another authority for managing navigability and the big rivers, which is federal. How does it intersect with the states? I think that there are difficulties there, and well, I think they will remain, I think.
Hello. Thank you for the presentation.
Okay.
I just have a question of would we, as part of the outcomes of this study, to have an estimation of the probability for of nearby culverts or ditches based on land use and the density of the land use? So something simple like, if this is the land use, this is the density of cars, trees, like trash bins, whatever, this is the probability that nearby ditches will be clogged?
That's what we would like to have. That it's in the urban fabrics to understand the probability of some streets and culverts, whatever, the probability of them being clogged. That's what we would like to go. And then, of course, we have a first idea of this urban area, red flags that can be clogged, and then actions to reduce the probability of being clogged. Okay, I think it will be a change of paradigm, but that could be very nice, I think. But it's very hard. Okay, it's even for the companies to do this. I don't know. Okay.
Thank you for the presentation, to Mario. I was just the stability curve you showed, H depth versus velocity. Like, did that come from your model, hydrodynamic model, or?
No, it's just so you have a piece of debris, and then we tested. Okay, we imagine floatability, movement like drag. We didn't call it like that. Sliding and toppling. And we just have, we have a piece, and we tested several water depths and several velocity against the most exposed area. But
so these are empirical data, like experimental data.
Yeah, just okay. Imagine that there is velocity in this. Okay, so it's questionable, of course, but okay.
Okay, and so the debris, like, was it that graph you showed? Was it? If you can go back to the slide, is it for? This one. So the F, right? Is it universal for all types of debris, or?
No. So let me go back. So we started by we have one curve for each one of these elements. Okay.
Okay.
So we start by looking what's there, and then we pick up on that. And we did this. And of course, some have more uncertainty than others. So these are the individuals, and these are all of them together here.
Okay.
And we have this for the other types of debris, for wood trunks, for other things. Okay, so there are several of these.
Okay. So several separate for each.
Yes, I didn't put it here because
each types of structure. I see.
But of course, some of them are much more uncertain than others, and then like small rubbish, it's much
I see.
But that's why we are now starting a new project with the university in Spain, because they have a street, they can put precipitation and flow, and we are start studying small things like this and plastic bags and things.
I see. I know these are all structure. I mean, I know you are calling like the vehicles and everything as debris, but also like I'm just trying to see, like, did you think of like the duration of inundation can affect these in any way?
The stability not, but of course the transport it will affect. But that's the next step. Yes.
Okay. I see. Okay. Thank you.
Okay, I think last question, and then apparently there's a reception just next door, so there'll be more opportunity to grill Mario.
Thank you. I have another question. So if I look at this figure, it seems like the small vehicle will be easily moved by the flow. That's basically the general trend. And if I'm a manager, I would consider to have less vehicle for some region they have a higher flooding risk. So how this funding can generate some like different managerial way for?
Well, this from here you don't go directly to flood to manage the urban area. I think it's more, for instance, pick up one of these. So now this is a kind of thing, a kind of large debris. And now you combine this with the flood and later with the transport. And then you will see with this condition of instability, with the conditions of transport that hopefully we'll be able to tackle as well. We provide a model, and we model them how they are transported, how many can clog a street or something. This doesn't serve for that, let's say. This is just an auxiliary curve for the transport. But then you can reach the conclusion that, okay, you cannot have this type of objects in that street, or you have to make parking that they are something like that. But for instance, you may have if you have a small street in the old part, in the old town, you don't have these big trucks for sure, you know. So some of them may not happen. If you have in the Netherlands, it's full of bikes, for instance. So it's. But this is another step of the characterization of what happens, what exists in the streets.
Would you consider the small vehicle to be a higher risk of conjunction or the big vehicle?
Well, you have a big vehicle and 20 small vehicles.
Yeah.
And the flood is not so big, so maybe transport the small ones. Okay, it's a combination of facts.
Yeah. So it's better to run the model.
I'm sorry?
So the message, like, it's better to build a model to give a more accurate.
No, you cannot. I think you cannot infer those conclusions from this.
Okay.
You have to have more knowledge or to model more. Okay.
Thank you so much.
Okay, thank you, Mario.
Okay, thank you for
very interesting.
Okay, thanks.